Okay, so let's consider several natural extensions for computing the MST for a graph. So, what to do with when the edge weights might be equal? So, a natural approach is to say, well, we can just add random noise to every weight. Think about just picking a tiny random number and just adding it for every weight, so that the weights become distinct. This is called sometimes perturbation. You can also do it symbolically. The details becomes complicated, and they're really not necessary in the MST case, because for the MST case there is a very simple solution. You just fix an order, a lexicographical ordering on the edges, right? You just say, the first edge is better than the second edge and the third edge in this order that you fix. And now you look for the MST that is first in this lexicographical ordering, right? Just think about now an MST as a word, right? The alphabet is just the edges. Every edge is a character. And you compare when you get an MST, you sort them by this order, right? So you have two words and you just compare them according to this ordering, right? This would be the ordering in the dictionary of those MSTs according to this underlying ordering of the edges. So this is called lexicographical ordering. You can induce it on any set, and then once you induce it on the set of elements, you can induce it. This defines the natural ordering on any subset of these elements. So we immediately get an ordering. And now that we have this ordering, so what happened? We have lexicographical ordering. We use the lexicographical ordering only when the two edges have the same weight, right? So if they are not the same weight, they are ordered by the weights. If they have the same weight, we order them according to the lexicographical ordering, right? Alternatively, you could just think about it that, we have an ordering of the edges, and this ordering is arbitrary, and we run the algorithm on this ordering, right? If you think about it, the MST algorithm, all it cared about was the ordering of the edges, right? It cared about whether you insert an edge according to the ordering, whether it was connecting two connected components that were separate, or the same connected component if you think about Kruskal algorithm. So all it cared about was ordering. So we really don't need weights on the edges when you compute MST. You just really need ordering. And under this definition, first, this allows us to handle case where the weights are the same, but that also allows us to do arbitrary ordering. Now, it's not completely clear why it's interesting, but from our purposes, the important thing is that once we do this modification of if two edges have the same weight, we use the lexicographical ordering. Under this new definition, all the algorithm we saw are essentially optimal. So that's nice. Okay, what about positive and negative, right? If we allow arbitrary weight. So the MST algorithm, as I just said, and if you look at it, doesn't care about the weights. It only care about the relative ordering. So if edges are negative, that's fine. Just run the algorithm. The algorithm just use the weights to order the edges. That's the only thing it does. So the algorithm works perfectly well with negative weights. This in particular means that all the weights can be negative and you're looking for the minimum spanning tree. But this is equivalent, if you think about it, where the weights are all positive and we are looking for the maximum weight MST. So we can compute the maximum weight MST, not only the minimum weight MST, which is kind of cool. That, of course, doesn't work with shortest paths, right? Why doesn't it work with shortest path? Well, we are back to our old nemesis of negative cycles, right? That if a negative cycle, we go around and around. If we are trying to look for the maximum length shortest path, then we are looking for essentially, again, we have to avoid cycles and we don't really know how to do that efficiently in general. Okay. By the way, if the weight of the edges are negative, one way you can think about it is that you add a weight for all the edges to make them positive and then run the regular MST algorithm. And the thing is, because MST has -1 edges, and you're adding delta, then the weight of the MST moved by the same amount, right? The MST is now positive, all the edges are positive when you add delta to every edge. You compute the MST and you know that the total weight had increased by at most this term, right? So this is another way to see that why MST algorithm can handle negative weights. Okay, so really I think the conclusion is that MST algorithm really care about the ordering of the edges. It doesn't care about the real value associated with them. And as such, it can work in any situation where you can define a good ordering of the edges.